Okay, so when I was working through the last example, there was a point in the computation that I wrote something down that I wanted to reemphasize. And it's an important piece whenever you're computing the area of these rectangles to approximate the area under a function. And in particular, it is the width of each piece. Because the width of each piece is very important because, I mean, well, hell, it is literally the width of each piece, each rectangle that you're dealing with. And the width of each rectangle is going to be completely important when you're talking about the total area of the rectangles, because the width times the height dictates the area of the rectangle. And remember, the width of each piece, well, as it calculated out to be, was simply computing the total width and dividing by the number of pieces. Because if the total width is whatever it is, and then you divide by the number of pieces, that's going to give you the width of each piece. So width of each piece is total interval width divided by number of pieces. No sweat. We'll actually see that in play here in this problem. And here, look, we're considering the function 1 over x. I didn't even write this as in functional notation, but consider that 1 over x is our function. And now what we are going to do is estimate the area under the curve. Now, when we talk about the area under the curve, this may be a shorthand notation here, but the area under the curve is this is the area between the curve and the x-axis. And we are going to do this for the function 1 over x between 1 and 2. We're going to use 8 subintervals. So we're going to chop into 8 individual pieces, which means we're going to have 8 rectangles. And we are going to use right endpoints along each interval, because along each interval you have a bunch of points to choose from. What point are we going to choose? Just to be conventional along the way so that we do this in a regular pattern, we're going to pick the right endpoints the entire way. So let's cook this up, okay? Now, to get a picture of what's going on, let's just look at our interval. Whoops, I put 2 there. 2 would be the right piece of the interval, 1 would be the left. Okay, here is our interval. Our interval is between 1 and 2. Now, how many subintervals do we need? We need 8 subintervals. So to get 8 pieces out of this piece, how are we going to do it? 1, figure out your total width, and your total width of your interval, in this case, 2 minus 1. In any case, it would be bigger number minus smaller number, b minus a in general. That would be 1. And then the width of each piece, the formula that we discussed at the beginning, which is up above, the beginning of this video, I suppose, that it would be total interval width divided by number of pieces, so 1/8. Each piece is an 1/8 wide. So we go from 1 to 1.125 to 1.25 to 1.375 to 1.5 to 1.625 to 1.75 to 1.875 to 2. 1/8, by the way, is 0.125, and 0.125 added in succession. 2 of those will give you a fourth, 4 of those will give you a half, 6 of those will give you 3/4, and well, 8 of those will get you a whole. And that's precisely what we see delineated here. But the long story short is no matter what those x's are along the way, and I guess this is not the long story short, but this is a takeaway here at this point, each piece, in terms of the width here of each piece is 0.125. That's going to be important because since each subinterval has a width of 0.125, each rectangle is going to have a width of 0.125. And now, the question is, since we know the width of each rectangle, what's the height of each rectangle? And well, the height of each rectangle is going to be dictated by the function height. How tall is the function tall at each of these points? Well, what point are we going to look at? Because to look on the first interval, we could look anywhere between 1 and 1.25. What x value are we going to choose? Well, we were asked to look at right endpoints. So right endpoints, we're asked to look at 1.125, because 1.125 is the right endpoint of the first subinterval. So we are going to build this rectangle to be as tall as the function would be tall at 1.125. The next rectangle is on the next interval. Its height is going to be dictated by the right endpoint. The right endpoint is over at x equals 1.25. What's the height corresponding to x equals 1.25? That's going to be f of 1.25. And now, you're going to do the same process all the way down until you get to that last guy. Let's just focus on him for a second to remind ourselves. What value are we going to use along the x-axis to dictate this? Are we going to take the left endpoint, the right endpoint, anywhere in between? Well, we're going to take the right endpoint because that was our convention. So of all the values between 1.875 and 2 along the x-axis, we're going to pick the value 2 because that is the right endpoint. And so the height of this rectangle is however tall the function is tall at x equals 2. That's namely f of 2. And now we can play the game here to determine the area of all these rectangles. It's going to be 8 rectangles. It's going to be a lot of numbers, but we can add them up, get the solution, and then have an estimate for how much area is under a curve, which is like kind of cool because this thing, this 1 over x curve, is actually not straight. A straight line would be in the form y equals mx plus b. So we are estimating the area under an object that is itself not curved. We're sort of finding the area of a blobish region, or at least estimating it as best as we can. Okay, so what's the area going to be? Look, the area under the curve, or well, in particular, our estimated area under the curve, is just going to be a sum of the areas of our 8 rectangles. So our first rectangle is going to be 0.125 times f of 1.125. Our next rectangle is going to be 0.125 times f of 1.25. 1.25 is the right interval on the next endpoint. What's the right interval on the subsequent interval? The subsequent interval goes from 1.25 to 1.375. The right endpoint is 1.375. So we are going to build that rectangle as tall as the function is tall at 1.375, which is precisely f of 1.375. And the next interval, the function height considered is the function height at the x of 1.5. The next function height is the function height at an x of 1.625. The next function height is the function height at f of 1.75. That's x equals 1.75. How tall is the function there? And then 0.125 times f of 1.875. And then 0.125 times f of 2. And now, each of these is a number. Each of these we're going to add together, and that is going to give us the total area. Now, to do each of these numbers, we're going to have to do a computation. So we're going to have to compute 1 over x. So in the first case, 1 over x, right? We're trying to compute here f of 1.125. Well, f of any x is just 1 over that x. So in this case, it's going to be 1 over 1.25. And check it out, we just calculate it away. These problems can get a little computational, but so what? This is going to be, when we run the numbers on this, I got the eraser right here. This is going to be 0.889. Fine, it is what it is. That's what the function height is at 1.125 for x. What about the next guy? The next guy is, what is the function height at 1.25? So f of 1.25 is what? 1 over 1.25. So I'm going to type in my calculator 1 divided by 1.25, and I'm going to get 0.8. So here's the function height here, 0.8. So be it. It is what it is. And what's next? Function height at 1.375. Since the function takes your x and puts 1 over it, or gives you back 1 over it, I'm going to get 1 over 1.375. That's 0.727. Next, 1.5. So the function is going to give me back, as always, 1 divided by whatever the x is. That's 1 divided by 1.5. That's 0.667. Next, 1.625. What is 1 divided by 1.625? That is 0.615. 0.615, whatever it is, no sweat. That's simply the height of the rectangle at that interval of interest. The interval of interest next, we're looking for the function height at 1.75. So I'm going to divide 1 by 1.75 because our function takes 1 divided by whatever our x is. That's 0.571. Next, we have the function height at 1.875. So I'm going to divide by 1.875. That's going to give you 0.533. And f of 2 is actually not bad, fortunately, because 1 over 2, the function gives you back 1 over whatever you gave it. 1 over 2 is 0.5. And now, guess what? We want to know the area. What do we need to do? We need to take 0.125 times this number, and 0.125 times that number, and 0.125 times the other number, and 0.125 times the other number, 0.125 times the other number, and then add them all together. And well, I mean, it's going to be a lot of numbers to crunch, but we can do it. And I tell you what, if you think about it for a little second, since each of these numbers are being multiplied by 0.125, all you got to do is factor out the 0.125 and then just multiply by 0.889 plus 0.8 plus all the way out to 0.5. Because you see, this is going to give you the same number. Since every number here is being multiplied by 0.125 and added together, you could factor out the 0.125 and then only have to add the other numbers together. So let's do that. I'm going to add all these decimal numbers together. 0.889 plus 0.8 plus 0.727 plus 0.667 plus 0.615 plus 0.571 plus 0.533 plus 0.5. Okay, that came out to 5.3. So 5.3 was, 5.302, I guess specifically, was the sum of all of those decimal numbers other than 0.125. The 0.125 needs to be multiplied by all of them in sum. So that 0.125 that we distributed out, now we multiply in, and boom, 0.66275. Here is an estimate for the area under this curve between 1 and 2. This is not a straight line, this 1 over x, so this area between this function and the x-axis is not a cookie cutter figure, yet we computed an estimate of it, and well, that's kind of cool, and at this point, that's all we got to be able to do.